It's given that a signal x of n is equal to sine of omega naught n is periodic. We have to find the condition on omega naught for x of n to be periodic. We know that as x of n is periodic, x of capital N plus n is equal to x of n. This should be satisfied for every n, where n is the period of the signal. From this, we can write that sine of omega naught multiplied by n plus n is equal to sine of omega naught n. This is equal to sine of omega naught n plus 2 pi k, where k belongs to z. From this, we can write that for x of n to be periodic, omega naught n is equal to 2 pi k, or we can write that 2 pi by omega naught is equal to n by k. From this, we can see write that for the given signal to be periodic, 2 pi by omega naught should be rational number. Now, let us consider another problem in which there is a discrete time system which is written as y of n is equal to x of n minus n naught plus e power x of n, where n naught belongs to z plus. We have to find if the system is linear, causal, time invariant, stable, and memoryless. The given system doesn't satisfy superposition principle, that is the linear combination of inputs is not equal to linear combination of outputs. From this, the given system is linear. Also, we can see that the output y of n for every n depends on past x of n only. From this, we can see that the given system is causal. Sorry, actually the output depends on past x of n and present x of n also. So from this, we can see that the given system is causal. As the output depends on past x of n also, the given system has memory. We can also see that y of n minus n naught, that is delayed version of output, is equal to, or rather say x of y of n minus n dash, that is delayed version of output, is equal to output due to delayed version of input, that is transformation of x of n minus n dash. From this, we can see that the system is time invariant as well. For checking the bounded in BIBO stability, let us assume that mod of x of n is less than or equal to b of x, that is the input is bounded. From this, we can also show that mod of y of n is equal to mod of x of n minus n naught plus e power x of n. This is less than or equal to mod of x of n minus n naught plus mod of e power x of n. So this is less than or equal to bx plus e power bx. As bx is finite, bx plus b power bx is also finite. From this, we see that the system is stable in BIBO sense. From this, we see that the given system is nonlinear, causal, has memory, time invariant, and is stable in BIBO sense. Now, let us consider another signal. X of t is equal to sine t plus sine of root 3t. We have to find if the signal x of t is periodic. If it is periodic, we have to find the time period of the signal as well. We see that the given signal x of t has two subsignals. First one is sine t, which is at a frequency of omega n is 1 is equal to 2 pi, and the second signal sine root 3t, that is at a frequency of omega 2 is equal to, sorry, the first signal is at an angular frequency of 1, the second signal is at an angular frequency of root 3. From this, we see that if we find omega 1 by omega 2, which is 1 by root 3, this is not rational. So as the ratio of angular frequencies is not rational, from this we see that the given signal x of t is not periodic. There is a list of attributes given in list 1 and the list of systems given in list 2. The attributes given are linear, time invariant, and stability, and the systems given are y of n is equal to e power sigma m equal to minus infinity to n x of n minus m, y of n is equal to n into x square of n plus 3, y of n is equal to n multiplied by sigma m equal to minus infinity to n x of n plus m. We have to match the attributes in list 1, that is PQR, to the systems in list 2, that are 1 to 3. From this we see that if we see the system 1, that is y of n is equal to e power sigma m equal to minus infinity to n x of n minus m, x of n minus m, we see that the given system is nonlinear as it doesn't satisfy the superposition principle, and it is time invariant, and it is not stable. From this we see that q maps to 1. Similarly, if you pick the system in 2, that is y of n is equal to n into x square of n plus 3. From this we see that as the system doesn't satisfy superposition principle, the given system is nonlinear and is also time variant, and we can also show that the system is stable in VIBO sense. So that implies R maps to 2. Finally, if you consider the system, y of n is equal to n multiplied by sigma m equal to minus infinity to n x of n plus m. From this we see that the system satisfies superposition principle, so it is linear, and also the system is time variant, and because of the factor n, the system is not stable in BIBO sense. From this P maps to 3. So we could match the attributes in list 1 with the systems in list 2. Now let us consider a signal e power t into u of t. We have to find if this signal is energy signal or power signal. So first we find the energy of the signal as Ex is equal to integral minus infinity to plus infinity mod of x of t whole square dt, that is equal to integral 0 to infinity e power 2t dt, that is equal to e power 2t by 2 infinity to 0. From this we see that this integral value tends to infinity, so we can say that the given signal is not energy signal. Similarly, we can find the power of the signal as px is equal to limit t tends to infinity 1 by 2t integral minus t to plus t mod of x of t whole square dt, that is equal to limit t tends to infinity 1 by 2t integral 0 to t e power 2t dt. This can further be simplified as limit t tends to infinity 1 by 2t e power 2t divided by 2, limits being t to 0. This is equal to limit t tends to infinity 1 by 2t e power 2t minus 1. From this we see that this limit value will also tend to infinity as t tends to infinity. So from this, the signal is not power signal. So we see that the given signal e power t into ut is not energy signal and it's not power signal as well. Now let us consider another signal x of t is equal to sine of root 3t plus sine 5 root 3t. We have to find if the signal x of t is periodic. The given signal x of t has two subsignals, of which the signal 1 is at an angular frequency of root 3 radians per second, and signal 2 is at an angular frequency of omega t equal to 5 root 3 radians per second. So if we find omega 1 by omega 2, we get a value of 1 by 5, which is rational. From this, we see that the given signal x of t is periodic. There is a signal f of t and g of t which are given as shown in the figures. Here, the function f of t is in the period of 1 to 3. It's a rectangular pulse having an amplitude of 1, and the signal g of t is a rectangular pulse. It's in the period of 0 to 1 and it has an amplitude of 2. We have to find g of t in terms of f of t. To get the same, first advance f of t by 1, then we get f of t plus 1 as shown in the figure, which would be in the period of 0 to 2 and it has an amplitude of 1. Now shrink along time scale by a factor of 2 to get f of 2t plus 1, which would be in the period of 0 to 1 and having an amplitude of 1. It's a rectangular pulse. Now amplitude scale f of 2t plus 1 by 2 to get 2f of 2t plus 1, which is a rectangular pulse in the period of 0 to 1 and has an amplitude of 2, which is identical with g of t. From this, we can write that g of t is equal to 2 times f of 2t plus 1. Now, let us consider another problem in which there are four options given. The option A is y of t is equal to integral minus infinity to t x square of t dt, and option B is y of n is equal to sigma k equal to minus infinity minus 10 to plus 10 x of n minus k, and option C is y of t is equal to log of mod of x square of t plus x of t minus 1, and option D is y of n is equal to sigma k equal to minus infinity to n x of n minus k. Out of the four options given below, we have to find the system which is linear and unstable. We can see that the option A doesn't satisfy superposition principle and is also not BIBO stable. Hence, it is nonlinear and unstable. If we see option B, we can see that from this it satisfies superposition principle, hence linear, and is also BIBO stable. And if you take option C, we can say that here the system doesn't satisfy superposition principle and hence nonlinear, and also the system is stable in BIBO sense. And if you take option D, in this case, the system satisfies superposition principle, so linear, and it is not stable in BIBO sense, hence unstable. From this, we see that option D fits the requirements. So option D is the one for which the system is, option D is the one where system is linear and unstable. Now Let us consider another continuous time system. Y of t is equal to x square of 2t minus 3. We have to find if the system is time invariant and causal, and also check anti-causality of the system. We see that here the delayed version of the output is not equal to the output due to delayed version of input. So the system is time variant. We also see that here the output depends on past and future values of samples for different values of t, that is for t less than or equal to t and t greater than or equal to t. So the system is not causal and not anti-causal as well. From this, we see that the given system y of t is equal to x square of 2t minus 3 is time invariant, not causal, and not anti-causal. Consider a signal f of t which is given as cos of zero point 0.8 pi t plus cos of pi t plus cos of 2.2 pi t. We have to find the time period of this signal. We see that f of t is a sum of three signals which is which are cos of zero point 0.8 t, cos pi t, cos 2 point t. We have to find the time periods or individual time periods of each of these signals, that is t1, t2 and t3. Now the time period of f of t is given as least common multiple of t1, t2 and t3. From this we can see that for the signal 1 the angular frequency is omega 1 is equal to zero point 0.8 pi, which can be written as 2 pi by t. From this we see that t is equal to 5 by 2 second. Sorry, t1 is equal to 5 by 2 second. Similarly, for the signal 2, the angular frequency is omega 2 is equal to pi, which is equal to 2 pi by t2. From this, the time period of the second signal is t2 is equal to 2 seconds. Similarly, for the third signal, the angular frequency is omega 3 is equal to 2.2 pi, which is equal to 2 pi by t3. From this, we can write that t3 is equal to 10 by 11 second. So, from this, we can see that the overall time period of the signal t is equal to LCM of t1 comma t2 comma t3, that is equal to 10 seconds. From this we see that the fundamental time period of the signal is 10 seconds. Now let us consider another problem in which there is a continuous time system which is given as y of t is equal to integral minus infinity to t x of t minus 2 tau d tau. We have to characterize this system based on linearity, time invariance, causality or anti-causality or non-causality, stability, memoryless property. Now we see that the given continuous time system satisfies superposition principle, that is linear combination of inputs gives linear combination of the outputs. From this we can say that the system is linear. Now for checking the time invariance, let us consider delayed version of output, that is y of t minus t naught, which can be written as integral minus infinity to t minus t naught x of t minus t naught minus 2 tau d tau. Also, the output y1 of t due to the delayed version of input can be written as integral minus infinity to t x of t minus t naught minus 2 tau d tau. From this, we see that the delayed version of output is not equal to the output due to delayed version of input. So the system is time invariant. Now we see that for t less than 0, y of t is integration of x of t over minus infinity to t. Sorry, y of t is integration of x of t minus 2 tau over the integration interval minus infinity to t. From this, we see that y of t is actually the integration of x of t minus x of t over the interval minus infinity to minus t. From this, we see that the output y of t depends on future values of input. Similarly, we can show that for t greater than 0, the output y of t is integration of x of t minus infinity to minus t. So y of t depends on only past input. From this, we see that the system is not causal, the system is not anti-causal, and hence non-causal. The system is non-causal, not causal because it depends on future input. The system is not anti-causal as it depends on past input. Hence the system is non-causal. We also see that as the system is non-causal, it has memory, so it is not a memoryless system. Now, to check the BIBO stability of the system, let us assume that the input to the system is bounded, that is, mod of x of t less than or equal to bx. From this, we can see that mod of y of t is less than or equal to integral minus infinity to t mod of x of 2 minus tau d tau. But we know that this mod of x of t minus t tau is less than or equal to bx, where bx is finite and non-zero, or rather say bx, sorry, actually here bx is finite. But from this we see that as the integration is from minus infinity to minus infinity to t, we cannot say that mod of y of t is less than by. This cannot be assured. From this we see that the system is not stable in BIBO sense. There is a discrete time system given with the input output relation as y of n is equal to x square of n minus 2 divided by 3 truncated. We have to find if the system is linear, that is L, time invariant div, causal C, stable S, memoryless ML, and invertible I. For the given system, we see that superposition principle is not satisfied. That is, the linear combination of inputs wouldn't give linear combination of outputs. From this, we see that the given system is nonlinear. Also, we can say that the delayed version of output, that is y of n minus n naught is equal to x square of n minus n naught minus 2 divided by 3. This is by replacing n by n minus n naught. Similarly, the output y dash n due to delayed version of input can be written as x square n minus 2 divided by 3 truncated minus n. From this, we see that the output due to delayed version of input is not equal to delayed version of output. From this, we see that the system is time variant. Also, we see that for n less than 0, say for n equal to minus 10, y of minus 10 can be written as x square of minus 4. That is, the output depends on future input. Similarly, for n greater than 0, say for n is equal to 14, we see that y of 14 is equal to x square of 4. That is, the output depends on past input. From this, we see that the output for some n depends on future input, and the output for some n depends on past input. From this, we see that the system is non-causal and not anti-causal as well. As the system is non-causal and non-anti-causal as well, we can say that the system has memory. Also, if we assume that the input is bounded, that is mod of x of n is less than or equal to bx, where bx is finite, we can say that mod of y of n will be less than or equal to bx squared. This is for every n. From this, we see that the system is BIBO stable. Finally, to check the invertibility, we can see that x of n minus 2 by 3 truncated can be written as square plus or minus square root of y of n. From this, we see that due to the sign factor or due to the ambiguity in the sign, we may not be able to recover the input completely for the given output. From this, we see that the given system is non-invertible. So finally, we can say that the given system is non-linear, time variant, non-causal, not anti-causal, has memory, BIBO stable, and is non-invertible. Now, let us consider another problem in which there is an input or a discrete time signal given as x of n is equal to 3 by 2 for n greater than 0, minus 1 for n less than 0, and 0 for n equal to 0. It is also given that there is a derived version of x of n, which is y of n is equal to x of n minus x of minus n. We have to find y of n in terms of unit step function u of n and impulse function delta of n. From this, we can see that the given x of n can be written as 3 by 2 multiplied by u of n minus 1 minus u of minus n minus 1. From this, we can see that x of minus n can be written as 3 by 2 multiplied by u of u of minus n minus 1 minus u of n minus 1. So from this, we see that y of n is equal to x of n minus x of minus n can be written as 5 by 2 u of n minus 1 minus 5 by 2 u of minus n minus 1, which can further be reduced as sorry. So from this, we see that the given y of n is obtained in terms of the unit step function u of n, but it's a delayed version of u of n that we used here. So the y of n is written in terms of u of n minus 1 u of n minus n minus 1 as required. We have to find which of the systems given in the options is linear and time variant. The systems given are in option A, it is y of n is equal to x of n plus 3. In option B, it is y of n is equal to x of n square. In option C, it is y of n is equal to x square of n. In option D, it is y of n is equal to sine of x of n. If we pick each of the system in option A doesn't satisfy superposition principle So it is non-linear, but here we can see that the delayed version of input would give a delayed version of outputs. So the system is time invariant system. So this is not the required system. And if you put the option B, we can say that here the system satisfies the superposition principle. So the system is linear. Also, we can show that the system is time invariant as delayed version of input doesn't give delayed version of output. So this is a required system. However, for continuity sake, let us check the option C and D also. If we see the system in option C is y of n is equal to x square n, here the system doesn't satisfy superposition principle. So it is non-linear, but here we can see that the system is time invariant. So this is also not the required one. And the system in option D is y of n is equal to sine of xn. This also doesn't satisfy superposition principle, so it is non-linear. And we can show that the system is time invariant in this case, as delayed version of input gives delayed version of output. From this, we see that the system in option B is the correct system, which is as per the requirements that system should be linear and time invariant. Now, in the next problem, there are two signals given. They are x1 of t is equal to e power j 30t and x2 of t is equal to e power minus 3 plus j whole multiplied by t. We have to find which of these signals are periodic. The signals given are x1 of t is equal to e power j 30t and x2 of t is equal to e power minus 3 plus j whole multiplied by t. The signal x1 of t can be written as x1 of t is equal to e power j30t, which can further be simplified as cos 30t plus j sin 30t. We see that cos 30t has an angular frequency of omega 1 is equal to 30 radians per second. From this, the time period of the signal is t is equal to 2 pi by omega, that is equal to 2 pi by 30 seconds. Similarly, the signal sin 30t is also periodic with a period of t is equal to 2 pi by 30 seconds. From this, we see that the signal x1 of t is periodic with a period of 2 pi by 30 seconds. Now let us pick x2 of t, which can be simplified as e power minus 3t multiplied by cos t plus j sin t. Here we see that because of e power minus 3t, the signal x2 of t is not periodic. From this, we see that out of the given signals, the signal x1 of t is periodic and the signal x2 of t is not periodic. Now, let us consider another problem in which there is a signal given as x of n is equal to 0 for minus 4 less than or equal to n less than or equal to minus 2 and it is equal to 3 otherwise. Now, there is another signal given, that is x of minus n plus 2 divided by 3. We have to find the range of n for which x of minus n plus 2 by 3 is not equal to 0. We can see that for the signal x of minus n plus 2 divided by 3 to be not equal to 0, the time index part, which is minus n plus 2 by 3, sorry, we have to find the range of n for which x of minus n plus 2 by 3 will be 0. So for x of minus n plus 2 by 3 to be 0, the time index part, that is minus n plus 2 by 3, should be in the range of minus 4 to 2. So from this we see that minus 4 less than or equal to minus n plus 2 divided by 3 less than or equal to minus 2. This can be reduced as minus 12 less than or equal to minus n plus 2 less than or equal to minus 6. This can further be reduced as minus 14 less than or equal to minus n less than or equal to minus 8. So this can further be reduced as 8 less than or equal to n less than or equal to 14. So for the time indices, that is 8 less than or equal to n less than or equal to 14, the given signal x of minus n plus 2 by 3 is 0. From this we see that 8 less than or equal to n less than or equal to 14 is the correct answer. As per the current problem, there is a continuous time signal x of t which is given as shown. So in the range 0 to 1, x of t's value is 2, and in the range 1 to 2, x of t's value is 1, and for t greater than or equal to 2, the x of t's value is like a ramp of unit slope. Now we have to represent x of t in terms of the unit impulse function delta of t, unit step function u of t, or ramp function t into u of t, or its delayed versions. We can see that x of t can be written as a sum of three signals, that is x1 of t, x2 of t, and x3 of t, which are as shown. x1 of t is a pulse in the range 0 to 1 of magnitude 2, and x2 of t is a pulse in the range 1 to 2, and it's a of magnitude 1. x3 of t is a ramp which starts at in the instant 2 from the value of 2, and it has unity slope. From this we see that x1 of t can be written as 2 times u of t minus u of t minus 1. x2 of t can be written as 2 times u of t minus 1 minus u of t minus 2. Sorry, there shouldn't be u in this case, 2 in this case. Similarly, x3 of t can be written as t times u of t minus 2. U of t minus 2 is taken here because the ramp starts from the instant t is equal to 2 and present till t tends to infinity, and it is of unity slope. Now we can write x of t as a sum of x1 of t plus and x2 of t and x3 of t. So on adding the obtained three signals, we get x of t as 2 times u of t minus u of t minus 1 minus u of t minus 2 plus t into u of t minus 2. So we got the given signal x of t in the required form. Now let us consider another problem in which there is a signal x of t given as sine of pi t plus sine of 2at. It is given that the given signal x of t is periodic. We have to find the possible value of a for which x of t is periodic, and the values of a are given in the options a, b, c, and d as 22 by 7, root 3, 2, and none of these. We know that the given signal x of t would be periodic if individual signals are periodic. So for it, we know that the signal sin pi t is periodic and it has an angular frequency of omega 1 equal to pi radians per second. Similarly, we know that the signal sin 2at is periodic with an angular frequency of omega 2 equal to 2a radians per second. From this, we can see that the sum of the signals is periodic if omega 1 by omega 2 is rational, that is pi by 2a should be rational number. From the given options, we see that the options A, B, and C don't give or don't give a value of a for which omega 1 by omega 2 is rational number. So the correct option is D. Please note that here the option A, which is 22 by 7, wouldn't also lead to omega 1 by omega 2 to be a rational number. This is because of the reason that 22 by 7 is not exact approximation of pi, but it is a approximate approximation of pi, for which, due to which omega 1 by omega 2 wouldn't be rational for option A also. Hence, the correct option is D. Now, let us consider another signal. Y of t is equal to sine of pi multiplied by x of t. We have to find if this system is memoryless and invertible. We see that for the given system, the output at any instant t, that is y of t, depends on the current input only. From this, we see that the given system is memoryless. Also, we see that the given system can be written in the inverse form as x of t is equal to 1 by pi multiplied by sine inverse of y of t. From this, we see that we may not be exactly recover x of t from the obtained y of t because of the reason that sine of pi into x of t will have a sine waveform as shown. So because of which we see that at pi by 2 and 5 pi by 2 the values are same. From this we see that for the given y of t, we may not be exactly able to recover x of t. From this we see that the given system is non-invertible. So we see that the given system is memoryless, but it is not invertible.